Hello everyone and welcome to my channel, and I'll be discussing exponential growth and decay with calculus. So first let's discuss the law of exponential change. We use it to find exponential growth and decay. So right now I'm talking about the law of exponential change. And it pretty much states that if something is increasing or decreasing proportional to the amount present, and you know the initial amount, you can find what you're looking for in a function of t. So this is a keyword that you'll find in all growth and decay problems, that if something like radioactive material or a quantity or a population or money, right, that it increases, decreases at a proportional amount, or proportionally to the amount present, then you can use this law of exponential change. And the actual formula of the law of exponential change is y, which is the final amount, is equal to y0, or the initial amount, e to the power of kt, and that you use just a regular constant e. K is the rate constant, and t is time. Now, when we talk about k as the rate constant, when it's greater than 0, this is defined as a growth. And when it's less than 0, it's defined as a decay. So this is pretty much the law of exponential change. So if you have something that increases or decreases at an amount proportional, or proportionally to the amount present, and you know the initial amount, if you know y0, you can find an equation, or a function rather. You can find an equation at a function of t. So let's try an example. Let's say you have electricity draining from a capacitor at a rate proportional to its voltage. So again, electricity is draining from a capacitor at a rate proportional to its voltage, or to the voltage. So again, voltage is the present amount of electricity, and electricity is decreasing at a rate proportional to voltage, which is the amount of electricity present. So this is exactly the same wording, just written in a different, perhaps scientific application of the same thing. And in addition to this, we're given dV over dt, which is the differential equation of how quickly it's changing. So we're given this dV over dt, and we know that is equal to negative 1 over 40. So it's obviously decreasing, it's negative. And we're also given the initial, we're not really given it, but we are told that we can write the initial value as V initial, or V0. So we just have to do that at the end. So the first part of this problem is to solve the differential equation for V, and we'll use this for the notation of the original value. So in solving this for V, you notice that we have two different letters here. We have V and T. You want to take all the V's to one side and all the T's to the other side, because in the end when taking the integral, you can only take an integral of a single variable. So, and if we're finding the differential equation for V, we need to take the integral of both sides. So let's go ahead and do that. So dV is equal to R D. Just rewrite it and then we'll start. It's the same thing we written, negative 1 over 40 V, and then you take dt to their side, and then we take the v to this side. So then on this side, on the left side, we get 1 over v dv is equal to negative 1 over 40 dt. We take the integral of both sides, and I put the negative on this side of the integral as negative 1 is a constant, and we get negative 1 over 40 t, and on this side we know that that is the this is the integral of the natural, or the derivative of natural log is 1 over v, and we'll, of course, let's not forget our plus c, a constant, we'll have at the end. And then if we want to take if we want to find in terms of v or in terms of t what v is, we should take e to the power of both sides, because that will get rid of the natural log here, and we'll get something that ultimately looks like this. This is always our goal. So let's just do that. E negative t over 40 plus c, and we know that this plus c is actually can be taken to the front here, can be multiplied, and it'll still be the same thing. And not only that, you can also jump another step and say that this plus c is actually the initial value of the voltage. So there you have it, that's the equation for the voltage, looking very similar to this. And now we can use this equation that we found to solve anything else that we need to. So if it asks us how long will it take for the voltage to drop to 10% of its original value, all we have to do is, we know the formula that we found, just rewrite it here. And if we want to drop 10%, the initial is always 1. This will be 0.1, so basically 100%, 10%, e to the negative t over 40. And from here, you just take natural log of both sides, giving you this a negative t over 40, giving you that, and you just multiply that by 40 and a negative 1, and you get 92.1 seconds. So that's how long it'll take for the voltage to drop to 10%. Thanks for watching.